Okay, hi everyone. I'm Alastair, and this talk was co-written with my colleague Pierre-Andre, but I'm the one here presenting it. We both work for Codeplay Software. Codeplay Software is a company that implements heterogeneous compute languages for a range of parallel hardware. And what I'm going to be talking about today is taking heterogeneous compute open standards and how we put those on RISC-V. So for this talk, I'm considering RISC-V accelerators. So what I mean by that is on a system, you have some host CPU that runs the OS, runs a driver, and so on, and then you're offloading compute to some accelerator. GPU would be a common example of this working, but in this talk, I'm talking about a RISC-V device as the accelerator. The CPU might be RISC-V, but it could be anything really as far as this talk is concerned. So in a heterogeneous compute language, the user program is split between some code running on the CPU and some code running on the accelerator. And there already exists a range of mature standards for this kind of programming model. So what are those mature standards? So yesterday, there was multiple talks talking about ecosystem. There was 2 panels on ecosystem. For RISC-V, ecosystem is, of course, a hugely important topic. And the same is true of heterogeneous compute standards. So there's already an ecosystem of software out there, applications and libraries written to these standards that you probably want to be running on your hardware. So in this talk, the standards I'm talking about are SYCL 2020, which is a high-level open standard C++ accelerator programming model. And in this talk, the way we talk about implementing SYCL 2020 on RISC-V is via OpenCL 3.0, which is a lower-level open standard C accelerator programming model. So we're talking about layering standards on top of each other. So to do this, with Codeplay, we have something called the driver development kit, which is another layer that goes below OpenCL, and it provides the tools to help companies implement OpenCL and SYCL on their accelerator devices. So what is the driver development kit? Now, don't worry, this talk is not just going to be marketing, talking about Codeplay products. What I'm actually going to talk about is how we explain this driver development kit to customers and how we let them experiment on their hardware, particularly with RISC-V. And I'm going to have a RISC-V case study. Because you may be looking at this diagram and thinking, there's a whole lot of technologies on there, there's a whole lot going on, and it's quite hard to follow. And the truth is, it is. We've had to put a lot of work into explaining it. So what we have here on this diagram are a set of layers. At the top layer, we have open standards. Those are standards from standards bodies such as Kronos, or other vendor standards for interop with other companies, such as the Intel Level 0. And they're essentially external to Codeplay. We implement them within our software. We're very involved in those standards, but they're not something that Codeplay specifically provides. Then the second layer, the dark green boxes, we have a set of code that Codeplay provides. We provide implementations of those standards, but those implementations are written on top of the DDK interface. So the DDK interface is the third and fourth line, the yellow boxes, and they're how we map Codeplay code to customer drivers, customer compilers. Because in the bottom line, in blue boxes, we have code that the customer themselves provide, the code that's required to actually run things on a given accelerator device. So on this picture, we have 2 stacks, left and a right. On the left, we have the compiler stack. So to implement OpenCL and SYCL, there's 2 primary input kernel languages. There's OpenCL-C, which the programmer might use directly, or there's a binary IR format called SPIR-V. If you're taking the SYCL path for doing standards, then you're probably going through SPIR-V because you want your compiler to be using a binary format to talk to the lower levels. So in the Codeplay DDK, we use Clang for OpenCL-C, and then we have our own code for consuming the SPIR-V. And this sits on top of a compiler interface that we have, which specifies how to connect your LLVM backend to the code we provide, and provides a set of guidelines and pre-written compiler passes to help with mapping the code from the heterogeneous standard parallel model to your parallel hardware. In the right-hand side of the stack, we have the runtime part of the standards. So that's OpenCL 3.0, which SYCL would be on top of, or in the DDK we also support Vulkan 1.0 compute and Intel Level 0. We provide implementations of OpenCL on Vulkan, and we're investigating Level 0 at the moment. And again, to implement these standards on top of customer drivers, we provide an interface in a DDK. It's essentially a spec that you implement for your given driver. If you implement code according to our spec, then our code should just run on top of the DDK interface, and it should just work on your hardware. We do have an additional optional layer here, what we call the how, because we target multiple RISC-V devices, so RISC-V simulators, actual RISC-V hardware devices. And unsurprisingly, there's a lot of commonality between them. There's parts that need to be unique per device. There's also a lot that can be shared between them. So to do this, we have an implementation of a DDK on top of how, and then you write a custom how for your new RISC-V device. And I'll talk about that in our RISC-V case study in a moment. But like I said, that's a whole lot in one diagram. That's 5 different standards, a whole set of external tools. There's a lot going on here. So when we're talking to customers, and we're trying to say, hey, you want to support heterogeneous standards on your parallel processor, you could use our DDK. We need those engineers to understand what we're talking about, so they want to use our product. They know if they use our product, they'll be safe with an implementation and they'll be happy with the end result. So some of the things that are hard to understand here is potentially it could be a new concept for a customer engineer that we have an integrated compiler and runtime. Although we do have these 2 stacks, and they're separated because they could be worked on by different people, we do essentially integrate. So this is quite different from, let's say, a DSP programming model where you just compile your program for the DSP and then you run it in the DSP. Here we have some code that's running on the host CPU and some code that is running on the accelerator device. We also have compiler code to help map data parallel standards to your parallel hardware. So in RISC-V, for example, you might have the vector extension. We have already, in our reference implementation, done the code to map from the implicitly parallel model of the standard to RISC-V vectors. But there could be custom things about your hardware that you need to understand, or maybe you have some different kind of vector processor. Because even if you're not using a RISC-V processor, you can still look at our RISC-V reference to see, well, this is how we did it. So again, that could be something new for an engineer in a company to understand how to do this mapping of parallel programming to parallel hardware. And third thing that's quite difficult to explain with customers is essentially requirements. We, of course, have requirements documents. We document what's required of a hardware to support standards, what's required of a driver to work with DDK, and what's required of a compiler to be able to interact with the compiler passes we provide. But the reality is the requirements aren't a binary yes, no, this will or will not work. It's more of a sliding scale of how much work are you going to have to do to get a good result. So for customer engineers to be able to understand what the result will be for them, how much work they'll need to put in, they need to be able to investigate the suitability of our DDK for their hardware. So to do that, we created something called Click. So Click is a simple compute library. It's the minimum needed to run a compute kernel on an accelerator. And when I say minimum, I mean minimum. Like it's 5,000 lines of code, where the actual OpenCL and SYCL implementations are millions. This is just here for the customer to understand the general concept of accelerated compute on your device, and to be able to do immediate experiments with the drivers and compilers that they already have, without needing to do extensive integration work, just to get something working which sort of looks like a heterogeneous compute language, but with lots of cheating going on, just to get the experiment going in a matter of weeks. So this works with your existing driver and compiler. In particular, the kernels just use your existing C compiler. And we provide a handful of tests to go with this for things that we say, yeah, this is probably something you should try out because this is something that's difficult and something you should think about. But it's a small test suite on purpose because this is not something that you want to implement correctly for purposes of shipping. This is just to help you learn. So in Click, a kernel is essentially just a C function. We use hash defines to kind of add some OpenCL keywords. But essentially, in a heterogeneous language, there's built-ins to a language which hand over parallels implicitly. So here on the code sample, we have get global ID. In OpenCL C, that would say, where in the parallel space are you? But it knows that just implicitly. It's kind of magic in the compiler and the implementation. Here we have an explicit state, the item struct we pass in. So this is so that you can compile code with your vanilla C, C++ compiler. There's nothing special about this, it's just code. And then you can implement the interface as you think is sensible for your hardware and as helps you to learn. So in RISC-V, you might think about how would I map this parallel set of work to different hearts, or how would I map it to vectors, or so on. An example on the screen, there's no parallel mapping at all, it's just a serial loop executing over all the work. So I'm going to go through a few slides of a case study where we implemented Click ourselves on the Intel Pathfinder for RISC-V FPGA product. So here, on the left-hand side of the diagram, we have the Intel Stratix FPGA, where we run the Intel Pathfinder harness for RISC-V. In the sample, we're running an Andes NVX27V softcore. And to interact with that software and to interact with the FPGA, what we actually have here is a daughter board on the FPGA that we connect to a separate debugger that then we can program with OpenOCD. This is actually a very common way for us to be starting on a customer project. It might seem very direct on low level, but we'd like to be involved as early as we can, because if you can run your software as early as possible, you can start considering the software in the design of your hardware immediately. So for the Click implementation, essentially we just implemented those 5 samples using the Click interface on an OpenOCD client. I should say the kernels compile, but just essentially we just used a vanilla Clang RISC-V compile. To execute the kernels, we essentially send the data with OpenOCD and then set a breakpoint, run it. If there's a trap handler, we set the core executing. If there's a trap, it gets caught, and then we either keep on going or finish depending on what kind of trap it was. This may seem very basic. This definitely will sound very inefficient because we're doing polling, we're not overlapping work, so on. That's all correct. But again, Click is about just getting something working immediately, like as fast as you can. This took a couple of weeks to do in Pathfinder, mostly because we were learning about OpenOCD. And then you keep on going to move to a complete solution by taking the very basic Click experiments you did and then porting them to that HAL interface that I described for RISC-V earlier. The HAL interface lays out the minimal compiler and execution and memory requirements to be able to implement OpenCL and SYCL sensibly. And you also, at this point, need to start integrating a compiler. You can't just use this fake C Click language we have. You need to actually integrate your compiler into the runtime using the DTK compiler interface. So you can actually compile kernels as required. Then, because you're using a standard HAL interface within the DDK, we can just take our reference RISC-V platform in the DDK and just run it on top of a HAL. And in principle, at this point, you have complete SYCL support, and you can start doing optimization work. As the project progresses, you may well remove the use of a HAL to do extensive customization, such as doing graph execution or custom language extensions. But these are steps you can follow. The further you go into the project, the more you need to customize to get better performance. So in the case study, we did this second step. We replaced the Click implementation with, we ported the Click we did to the HAL interface, created the Intel Pathfinder HAL within the DDK. It's still running on top of OpenOCD because it's just like the Click, except with a compiler integration. And then here in this diagram on the right-hand side, everything above the HAL API line is just out-of-the-box DDK components. You get the OpenCL implementation, you get SYCL implementation, just works. And we can run some We can run overclock samples. They all work in the FPGA. And we can run about proof of concept level SYCL and OpenCL. So what we have here in the picture is Conway's Game of Life. This is the largest application we managed to run on the Pathfinder FPGA because at the current iteration we have some memory limitations. So that was the largest program we could fit in. The performance here is nothing special because this is the first thing we got working. This is just getting it working as quickly as possible. The optimization comes later. We're not using multiple hearts in the RISC-V core. We're doing all the data transfers over JTAG, which is obviously very slow. But we have a SYCL application working in a couple of weeks with using, well, it's a senior engineer who did this, but customers can do the same, especially if we're working for RISC-V, because we have so many of the RISC-V components pre-written. So what did we learn from doing this? We think that tooling to start investigations immediately does help. It helps engineers to understand how the skills they already have will fit into a new project for doing an acceleration implementation on their hardware. Because they may have been working on something else previously, and now they need to support something like SYCL on their hardware. Doing this investigation lets them feel comfortable that they will be able to complete this project successfully. We also pair the click demos with our full RISC-V reference stack running on some kind of simulator to be able to show you can run full SYCL applications. So the customer can see, yeah, if we do these small experiments, we can show things can work in principle and we can understand, and then we can see the full reference to understand where we can get to once we do all the work. And that works quite well because we have pre-written so much, and we think that's important for our product to pre-write as much as possible so as you can be functional as early as possible. Yes, a lot of the pre-written components we provide will get replaced as the project advances because you need to customize the implementation for your hardware, but that's fine. And this really helps with a software-first development approach where you're developing hardware to target your use case software. Because you can get it running early, you can do the experiments and start to actually measure performance and make changes as required. And the final thing I think we learned was that just because you've got standardized ISA such as RISC-V, it doesn't mean that everything will just work. Different RISC-V processors have different memory architectures. There's a talk yesterday about how one processor had all these configurations of different memory architectures that you can configure at runtime. Even RISC-V extensions go through iterations. So the hardware you're targeting, especially during the development stage of a project, because we're talking about very early stage hardware here, it may not be 1.0 yet. And you need to figure out how the heterogeneous programming models can map to this. And we think that the DDK helps for this. And RISC-V is a really excellent target for this kind of investigation because the core ISA is there, but you can figure out how to customize it yourself to target your own use cases. So thank you. Are there any questions?
All right, let me do a quick check in the community here, see if we have any questions online. I do not see any. We have a little over a minute. Any questions in the room? Of course, the person clear in the back. All right, here we go. I'll get my exercise.
Just one question. How many APIs does a typical HAL has for RISC?
I'm sorry, I didn't catch the question.
Typically, how many APIs are there in HAL layer of RISC-V?
EPAs?
APIs.
Oh, sorry. A lot, actually, because so SYCL, the high-level standard, is an API. We implemented OpenCL, which is an API. Then we have our DDK interface and potentially a HAL interface. And then in this case study, we're putting it on top of OpenOCD, so that would be 5 APIs, which sounds like a lot. And you'd think there might be overhead from that, but in reality, because you're offloading large chunks of compute, you get so much gain from doing the offloaded compute that the fact that you have to go through a few layers in the CPU doesn't make as much difference as you'd think. Of course, we put work into making sure it's cheap, in terms of performance, but
Okay,
Yeah.
thank you.
Other questions in the room? Going once. Going twice. Oh, yep. Clear on the other end, yeah.
How portable is this to other RISC-V implementations? You demonstrated there with Andes, but there are other cores out there. How portable is this method to these?
so within Pathfinder, it should be very portable because Pathfinder is designed as a development platform for RISC-V cores, so you should be able to plug them in. And even for RISC-V in principle, I don't think I can name them all, but we have done projects on other RISC-V processors. We've supported multiple RISC-V simulators through the same interfaces. It's extremely portable to different RISC-V processors, partly because it does have this base standard, but then the whole purpose of our DDK is to support custom hardware. So even if you've got a base standard and then you start customizing your architecture, you should be able to target all of that.
Okay, let's give Alastair one final round of applause, thanking him for his presentation. Thank you.